So let's talk about what we're going to work on today. Our last session, we learned about two special forms of distributions. We learned about the normal distribution. That's numbers that when we sample the population, the values are normally distributed. They are, they tend towards a central area. They tend towards a mean. Most people are close to that mean, that average. For instance, height, weight, most people are within a certain average range of height. As you get further and further away from that average weight, height, blood pressure, you have fewer and fewer people that fall into that range. So you typically will see a bell-shaped curve where most of the population is in the middle and fewer and fewer and fewer people are at the extremes. Okay, so, and we learned from the empirical formula that there's a special relationship between the average, the mean for the entire population, and the variability, the standard deviation for that population. And we learned that, for instance, that if it's truly a normal distribution, that 95% of the people in that population will be within 2 standard deviations below the mean and 2 standard deviations above the mean. It doesn't matter whether that standard deviation is, let's say the mean is 100. It doesn't matter if that standard deviation is 1, 10, or 20, because that rule still holds. In other words, if the standard deviation, the mean is 100, standard deviation is 1, then 95% of that population is between 98 and 102, 2 standard deviations either way. If the standard deviation is 5, well, then 95% of the population is between 90 and 110, again, 2 standard deviation. And if the standard deviation is 20, then it would be 60 to 140 and so on. So I think we can wrap our heads around that pretty easily. And we know also that 68% is between 1 standard deviation above and below, and 3 standard deviations. Well, almost all the entire population is within that range in a normal distribution. Okay, so that is a very useful tool for us. We then learned that we also have a calculation that we can make using the Z distribution, the Z table, the standard normal distribution, that allows us to predict, even if it isn't a whole number standard deviation, what percentage of the population is within a certain range, below a certain number, above a certain number, and so on and so forth. And we did that by going to the Z table and calculating what that area is. I'm going to try and install my, I'm using a school laptop here, and I've never used a graphics tablet on one of the school laptops, but I'm going to see if I can't get this to work so I can just do a little bit of sketching later on. If not, all is not lost, because really I'm moving on now to something called the central limit theorem. Okay, so what is the central limit theorem all about? Well, central limit theorem tells us that if we take a sample, if we take a single sample from a population, and most of the time we're dealing with samples, very rarely are we dealing with an entire population, right? Because it's very difficult to deal with an entire population. We'd have to measure every person in that population. For instance, if we're interested in BMI, we'd have to measure the weight and height of every person in the population to know what the average BMI for the population is. So rarely do we actually get an opportunity to work with data that's based on the entire population. Almost all of our life and statistics is going to be based on samples. Taking a random sample of a larger population and trying to predict what that population looks like. So when we take, if I took a sample of 10 people, randomly selected from a population of 100,000 people, let's say all the people in Staten Island. If I took a random sample of 10 people in Staten Island, I would take those 10 numbers, those 10 BMIs, I would average them, I would calculate a standard deviation. And that average and that standard deviation would approximate what the mean and the standard deviation for the entire population might look like. Well, the only problem is 10 is a very small sample, it's a relatively small sample. Now, if I took 20, a random sample of 20, I'd be in better shape. If I took a random sample of 30, I'd be even better shape. If I took a random sample of 100 people, I'd actually be in pretty good shape at that stage. Because once you get up in the numbers 100, 200, 300, you usually get a pretty good window on what the mean is, what the average, what the middle value is for a population, for whatever numerical variable you're looking at, and how spread out it is, what the standard deviation being a measure of spread. Okay, and then you can use that to make predictions about that population. What percentage of the population has a BMI below 25? What percentage of the population has a BMI above 30, and so on and so forth. Right. So we have a window on understanding how that works. If you need to, you can always go back and you can look at the videos from the online session on Monday. Did you guys get a chance to look at that? I know we didn't have too many people logged on, but I'm hoping that you guys got a chance to play those videos, or at least a couple of the beginning videos or a couple of videos to get a window on this stuff. Did you guys type into the chat box for me? How many of you guys actually got a chance to view those videos? I know it's summertime. I know the weather's wonderful. The beach is calling, but unfortunately, we are stuck here with biostatistics, and we need to keep up on this stuff. And the reason why I say that is because some of what I'm going to do now is based on what we did during that session on Monday. I'm going to back up. I don't exactly have people like falling all over themselves to type into the chat box that they watched all the videos. So I'm going to assume that I need to back up just a little bit to make sure that we have a handle on this stuff. Am I assuming correctly? Okay. Okie doke. Okay, so let me see if there's a way. Again, I'm working with I don't want to say a strange computer, but a different computer. So I'm a little bit hamstrung here. Let me see if I can't do something here to get a. Okay. Yeah, no, I don't think this is going to work for me. Okay, I'm going to have to do kind of wing it. Let me see if I can't get a whiteboard up here. Actually, I'm going to do that. I'm going to do this using Word. Probably be a little easier anyway. Okay, so let's take a look at this. Let's say that we have a situation where we have a population with a mean of 100 and a standard deviation of 10. If I were to ask you what percentage of this population has a value, whatever this is, weight, blood pressure, test score, or something like that, what percentage of this population has a score, a whatever this value is, I'm going to call it blood pressure. Let's say that the mean blood pressure of 100. What percentage of this population has a mean blood pressure between 90 and 100 and 110? Okay. So can someone answer that for me? How many standard deviations above and below the mean is 90 and 110? I know you can answer that question. Come on, so it's one of you guys type it in there. I'm dying here. I'm like a stand-up comedian that ain't getting any laughs. Oh, wait a second. I think that I'm not scrolling here. Okay. Hang on a second. I am getting some responses here. I just couldn't see them. Okay. Well, actually, it's one standard deviation above and one standard deviation below. Okay. So what percentage of the population does this actually represent? 90 percentage of, right, 68%. Remember our empirical formula told us that 68% of the population is between one standard deviation above and one standard deviation below. Oops, I'll do it this way. I'll put in -1 standard deviation. Okay, what about what percentage of population is between 80 and 120? Do I have a response on that? I know if you got the first part, you're going to get this next part too. Well, remember the empirical formula? 68% of the population is between one standard deviation above, and 95% of the population is approximately 95% of the population is between two standard deviations above and two standard deviations below, right? Or 80 and 120 in this case. Okay, and 99.7% is between three standard deviations above and three standard deviations below. In other words, 70 to 130. Okay, so we could figure each one of these out. 70 to 130 would be 99% of the population. The other way you could look at this is that if I asked you, what's the probability that that if you picked a random person out of this population, that their blood pressure would be between 90 and 110? And the answer to that would be, since 68% of the population is between those two numbers, the probability would be 0.68 or 68% that you would choose a person in that range. So what percentage of the population, what percentage of the population has a blood pressure that's less than 90? And we have to do a little bit of deduction there. You know, this doesn't scroll down and keep up. Oh, good. You guys are answering this stuff for me. Okay, right. 16%, right? Because if 68% is between 90 and 110, you're left with 32%. 32%, the normal distribution is symmetrical. So, you know, 16% is going to be below 90 and 16% is going to be above 110. Excellent. Okay, so now let's throw a little wrench into this and ask, what's the probability that you would randomly choose from this population an individual whose blood pressure was 85 or less? Okay, let's think about that. First of all, number one, how many standard deviations below the mean is 85? Right, we're going to go to this exactly. We're going to go to the Z table exactly here. Okay, so in this case, 85 is 1.5 standard deviations below the mean. Another way of expressing that for the standard normal distribution is we're saying that its Z-score, its number of standard deviations from the mean, is equal to, and I'm going to do the calculations here, going to be equal to the value we're interested in. It's going to be 85 in this case, minus the population mean over the standard deviation, or sigma. Okay, I can't type sigma, so I'll put that in there, over the population standard deviation. So that's Z-score. The number of standard deviations is 85 minus 100 over 10. Okay, it's 15 over 10 is equal to negative 1.5. So negative 1.5 standard deviations. So at this stage, I would need a way to tell how far below the standard, what percentage of the population is below that level, or what the probability would be that I would randomly choose someone in that area of the distribution. And we have a table for that. This represents a standard normal distribution. It's based on a distribution that has a mean of 0 and a standard deviation of 1. But the numbers, the areas that it gives you, will literally allow you to choose to determine areas in any part of the distribution. Okay, so I'm using this one. It's almost identical to the one in your textbook. If you like the one in your textbook better, you can use that. I don't know why it's doing that. Okay, good. Or why it's doing that. But let's see if I can explode this up just a little bit more. How about 75%? Yeah, I think that'll do for now. Okay, so we want to know what area of the distribution is represented by a z-score. You can see z over here. See it over here, right by this little sketch of a normal distribution. And this z-score, this table represents the area that's grayed out here, that's darker here. So whatever the z-score that is that we're looking up, it's going to return for us the area of the distribution that's below that value. It's from that value down. So 1.5 standard deviations, negative 1.5 standard deviations. First thing we know, it's below the middle, because the mean would have a standard deviation, would have a z-score of 0, right? So this is negative 1 standard deviations below, from the mean. Okay, so we're going to look at what this area must be, and that'll represent our probability. That'll represent the number of people in a population that are in that range, and it will also represent the probability that we would choose someone randomly from this population that's in that range. So the way we're going to use this is the z-score is listed in the column here, and the negative ones are in this first page, and the positive ones are on a second page. Notice the positive ones, that area is always above 50%, because the positive z values are always above, always going to be above 50%, because the mean, 50% of the population is going to be below the mean. So anything with a positive z-score is going to be more than 50%. You can see even 0 is exactly 50%. 0 and plus anything goes above that. So let's take a look at our 1.5. So here is 1.5. Well, next to this 1.5 for the z-score, we see not just one area represented, but 10 areas represented. And each of these columns represents an area that represents the third digit in our z-score. So in other words, this first column would represent, for instance, over here, this is 3.4. This first column would be 3.40. The next column would be 3.01, 3.41, 3.42, 3.43, and so on and so forth, right? So we're looking for 1.50. So 1.50 would be 1.5. Hard for me to see the cursor here. 1.5. Oops. And that would represent 0.0668. So the area to the left of negative 1.5 is 0.668, a little bit more than 6.5%. So if I go back to my document here, if I can find it. Oops. Right. The area, or the probability for blood pressure is less than 85, less than or equal to 85, you could say, is 0.0668. Okay, so that would give us, that's how we might manage this. Now, if I asked you what's the probability that a person's blood pressure is above 85, anybody want to hazard a guess? find out what's the probability. Since we know this, what's the probability that it's above 85? Well, if we're looking at this distribution, and the area that we're looking at is 6%, what percentage would that be left? What percentage of the population, or what percentage of this distribution would be on the other side of that line? Well, if it's 6%, then it's going to be, or 7%, then 93% of the distribution is going to be on the other side of that line. If you do it a little bit more accurately, it's going to be 1 minus 0.0668. Or let's see, that's going to be 2. 2. A little hard to do this way. 2, 3, 3, and 90, and let's see, 9. Is that right? 0.93. Where's that? Okay, 0.9332. Let me add those two together. 10 carried 1, 10 carried 1, 10 carried. That looks right. I believe that might actually be right. Okay, did you guys get it? Again, I have to scroll here on this machine in order to do that. Okay, good. All right, so we got a little bit of that. Yeah, 0.93 is close enough as far as good enough for government work for today anyway. Okay, so that's, this is valuable to us. We understand now that this can give us a lot, knowing the mean and standard deviation of population can give us a lot of information about a distribution. Unfortunately, as I told you before, we almost never have that advantage. We're almost always dependent on taking a sample from a population and extrapolating what we know about that population from that sample. It's intuitive that the bigger the sample is, the better off we are in terms of understanding more about that population, being more accurate about our predictions about that population. Okay, so I'm going to go over here and I'm going to go back to our document that we had originally, if I can find it with this silly computer. Okay, where's window? Let me see if I can't move things around here. You can't see me working on the control panel there, but that's what I'm doing there. Okay, let's go back here. Oh, not the one I want. Let's minimize this, get it out of the way. Here we are down here. Okay, examining the central limit theorem. What the hell is the central limit theorem? What does that mean, the central limit theorem? Well, since we're going to be working with samples from now on, we need to understand the dynamics of samples. What samples tell us about the population and how the size of a sample impacts our understanding of the numbers that describe that population, mean and standard deviation. So since we're interested in samples, it might be an advantage to us to understand what would happen if I repeatedly take samples over and over and over again. Okay, so I have a document on Blackboard. You guys can open it up as well if you want, where you can watch me working with it as well. Actually, at one point, I'm going to ask you to actually open it up and work with it a little bit. But I'm going to go here to, let's see, here's the Excel population. It's called population 100 or something like that. Population 100.exl, XLSX. Okay, so this is this set of numbers represents, let's see, let me get this up, make this a little bit smaller. Come on, give me a drop menu. Okay, so if we can fit them all in there. That works a little bit better. This set of numbers represents, actually I need to be a little bit smaller even. Let's go down to 60%. That works good. Okay. This represents, these black numbers in here represents test scores for 100 students. That's my population. My population is 100 students. Now, normally you're dealing with populations that are much larger. If you're in public health, you could be dealing with the population in New York, 9 million people. You might be dealing with the population in the United States, 370 million people or whatever we're up to at this stage, right? So very frequently you'd be dealing with very large populations. In this case, I'm going to simulate this with a population of 100. I'm going to say to myself, you know, I can't afford to sample to actually measure, get the score, take a score for every person that's in this population of 100, but I can afford to do it for 9 people, a sample size of 9 people. So I'm going to define my sample size here. Whoops. Nothing came out there when I typed. Okay, let's try and figure out why that's happening. Enable editing. That should help. Good, I think it will. So N is equal to, let's see, actually I put it into the next box. N is equal to 9. That's my sample size. So I am going to secretly do something that I told you we never know. We never know what the mean of this population. Actually, I'm not going to do that right now. What I'm going to do is I'm going to randomly sample 9 people from these 100 people. And I'm going to ask you guys to do exactly the same thing. Okay, the only problem is that it's nice to say that, right? But it's a lot harder to actually generate a true random sample. I'm going to pull the chat box out here so I can keep an eye on any comments. Okay. Okay, so I'm going to ask you guys to do this along with me. I'm going to choose 9 random individuals here. Okay, so how am I going to choose? How am I going to do a random choice? Am I going to do like, you know, open the phone book and just put my finger down, or look at the spin the globe and put my finger on the globe and say I'm traveling to whatever country that it winds up? Not a good idea in a lot of cases, right? How am I going to actually determine whether I have a random sample? Well, the way I've laid this table out, you can see that we have a series of rows, numbered 0 through 9, right? And we have a number of columns numbered 0 through 9. Okay, so we have 10 rows, 10 columns. So each person can be defined as a row and a column. So if I were to talk about a person that was number 27, row 2 and column 7, that would be the person. That person had a test score of 39. How about 31? 31 would have a test score of 49. How about 62? 62 has a test score of 62, and so on, right? So I could, if I had a way to do it, I could choose 9 people at random. Now, what I can't do is I can't just use my eye and finger to randomly pick people, because I'm going to introduce some sort of bias. If I'm right-handed, I may be more likely to pick people on the right side of this thing. If I'm unconsciously, I may be, you know, my attention might be grabbed by numbers that are larger or smaller for some reason. So I need a mechanism where I know I can sample randomly. There's many random number generators. There's programs that generate random numbers. There's software that generates random numbers. There's all sorts of techniques that generate random numbers. One simple way is that there are actually manuals that are published that will give you random numbers if you want them, okay? And there is one on Blackboard that is called Random Number Table. Okay, a little bit of explanation of how it's derived and what it is. But all it is a series of randomly generated numbers. Now you may say to yourself, well, look at that first number, 111. What are the odds of 111 coming up 3 times in a row, right? Well, that's what happened when this table was randomly generated. So you're going to have some repetition, just like you'll see, you know, red come up on the roulette table, you know, 4 times in a row or 5 times in a row. It's going to happen. You can flip a coin and come up with 4 heads in a row occasionally, not often, but occasionally. So it's going to come up every once in a while. So, but the point here is that these numbers were generated randomly. So you could actually start anywhere in this table. You can pick out a spot anywhere. I'm going to start right here. Okay. And from this point on, I'm going to let the table determine for me which person I'm going to choose. So person 39, right? 39. That person 39, that person's test score is 55. So I'm going to go to Excel. I'm going to, okay, we have Excel here. I'm going to go over here. And what did I say was 39 was 55? I'm going to put 55 down there. And now I'm going to go back to my table. And the next person is going to be 55. Okay, so 55, person number 55, row 5, column 5 is going to be 0, 1, 2, 3, 4, 5 is going to be 32. Okay, next person is going to be, let me go back here. Next person is going to be 57. Row 5, column 7, 0, 1, 2, 3, 4, 5, 6, 7 is going to be 52. Okay, what I'd like you to do is I would like each one of you to choose 9 numbers from this table randomly. Now, I'm not there to look over your shoulder, so if you want to say to yourself, well, I'm going to humor that old man, and I'm just going to pick them at random. I'm okay with that, just so we expedite the whole process. I'm going to choose 9 of these numbers. I'd like you to choose 9 numbers too. And after you've chosen the 9 numbers, I want you to find the average for the 9 numbers that you've chosen. In other words, the average for your sample. Okay, so I'm going to go continue with where I was at before. So let's see, where was I? Kind of lost track here. Well, I'll pick up over here. Row 7, column 4. Row 7, column 4 is 41. Next, so I'm going to depend on you guys to work on this with me. Okay, you guys okay with that? If you're having a problem, give me a little alert in the chat box, or if you don't understand what I'm doing. Okay, and next one, 7439, 3. I think I just chose 30. 39 would be 55. I don't know if they chose it before. I was just going to say it's with replacement, so I'm not going to worry about that. 39, 10, 1, 0. Okay, 1, 0, 65. Okay, and 7, 5, and 7, 9. 7, 0, 1, 2, 3, 4, 5, 47. And 7, 9 is 41. How many do I have so far? 2. I got 1, 2, 3, 4, 5. I think I got 7. I need to expand this so I can see it. What I do. I can't get to the corner. One, 2, 3, 4, 5, 6, 7, 8. I need one more. 7, 6, 9 is the next number. Come on, let me scroll over. 6, 9 is going to be 64. Okay, so I'm going to take the average of these numbers. Of this set of 9 numbers. 3, And the average comes out to be 50. And mean, I'm going to call that X bar. Okay, how about you guys? Guys, I need you to type into the box. I need some results from you guys. For sample size 9. So I'm counting on you guys to help me out with this. Okay, I'm gonna give you a few minutes to give this a try. What we're doing here is we're going to examine what happens when we take a sample of a certain size from a population. And what happens if we do it more than once with the same sample size? Are the results, the means that we're going to get for our sample? Notice I said X bar. By X bar, I mean an X with a bar over the top of it. It's easier for me to type that way. But each time I do this with nine randomly chosen people from this population, each time I do this, it'll be a repeat of a sample of size 9. So I want to examine how close, how variable, or how far from the true mean of the population my sample means are, how variable they are, how close to the true mean they are, because that may enlighten me about how samples behave. And how samples behave is going to be critically important to us going forward in this class, because and in your careers, because everything you do is going to be based on estimates and predictions based on samples, based on the results of small groups that you've chosen in a study from to represent a much larger group, much larger population. So I'm hoping you guys will type some stuff into the chat box soon. Like I said, oh, there you go. Okay, good. Let's see the other X bars. We got a 52, and we got a 53. Okay, anybody else? If I have to, I'll live with that. Okay, so what I'm going to do now is I am going to do what I told you we never get some information that I just told you that we never have, and that is I'm going to find out the average, the mean for the entire population. So the mean mu for this entire population is equal to the average for all of these numbers. Okay, the mean is equal to 50. I got lucky there. You guys got pretty lucky also. What's the standard deviation? What's sigma for this population? Well, sigma is going to be equal to the standard deviation for this entire population. Okay, and sigma was 9. The standard deviation of this population is 9. So what does that tell me? That tells me that 68% of this population is between 48 and 59. 95% of this population is between, 32 and 58. And so on. We could play the same games with the population that we did before with the standard normal distribution. Right now that I know this information about the population, I know a lot about the center of this population and how spread out it is. Now, these three numbers that I have here, those numbers are the sample, are the means for repeated samples of size 9. Remember, I'm gonna paste those over here. Those are, oops. Oh, you know what it is? I did a calculation, so I can't just do that. Let me see if I can't. Let's see. I'm gonna leave them there. Forget I did that. I'm gonna leave them there because I don't get hung up trying to figure out where to find all the functions on this particular computer. Okay, so these are my three means. That's X bar for one of us, X bar from another one. Did they get any more? Anybody else throw one in there? I don't think so. Okay. Okay. So let's take a look at this. First of all, the mean for our first sample was 50. The mean for a second sample is 52. The mean for a third sample is 53. Well, those means approximate the population mean. They do it pretty well, right? They're not that far off from the population mean. They're certainly a lot closer to the population mean than these individual values. Look, one time we picked one, that personality was 32. Another time's 65. Sometimes we got closer, 47. But look at all the variability in those numbers that we had there. The variability is, first of all, number one, these are relatively close to the true population mean, and the variability is much less than the numbers themselves. So what does that tell us? Number one, it tells us that X bar, right, approximates mu. The next thing it tells us is that if I were to take the standard deviation for my single sample, for just this one sample that I did, we take the standard deviation. Well, you know, standard deviation is 9 for the population 9. This is 11. It also approximates the standard deviation for the population. So standard deviation, I'll call it SD, approximates sigma for any one sample. But now look what happened when I took my sample means and I'm going to take my sample means now, and I'm going to take the average of my sample means. So I'm going to take a new sample, and that's going to be equal to the mean for this new sample, which is this new population, which is my repeated samples of size 9. So what's the average? The average is 52. Actually, it's these are this is rounding. I'm not going to bother to go in and change the rounding. That's interesting. So if I take repeated samples of size 9, when I average each one of those average, in other words, we have a new distribution that's based on repeated averages from a population of exactly the same sample size 9. Well, my mean for that new distribution, which is all sample means, it approximates my population mean. What about the standard deviation? Standard deviation for this new distribution. Okay, standard deviation, parentheses, for these numbers, which are the results of my sample means for repeated sample means, they come out a lot smaller. The variability in, if I would looked at repeated samples from a population of the same size, the sample averages for all my repeated samples approximates the population mean, but the standard deviation of my repeated samples is a lot smaller than the standard deviation for my population. In this case, it's a bit smaller than you would really expect. There's a very small group here. We only did 3 numbers. If I had when I would do this with a classroom full of people, we'd get a much better picture of what the standard deviation of repeated samples of size 9 is. Okay, now what's buried in here is a special relationship. What's buried in here is that the mean of our sample distribution, right, repeated samples, approximates the population mean. Okay, that's nice, but what's even nicer is now we can also say that the standard deviation of our sample mean, a sample distribution, which is, you know, this new distribution based on repeatedly thousands of times, let's say, taking a sample of size 9 and finding the average and making a new distribution out of that. The standard deviation of our new sample mean is equal to this. It's equal to the standard deviation of the population, sigma for the population, divided by the square root of the sample size. Okay. So technically, if I did a large enough sample, what would my standard deviation for repeated samples come out to be? If I did a large enough sample size, my standard deviation for repeated samples of size 9 should come out to be 9 sigma divided by the square root of 9, which is 3. So it should be 3. We got 1. It might even be 1.5 or something like that because it's truncated. Okay, so our standard deviation for our sample means is equal to 3. So if I were to do this over and over and over again, take that sample size 9, it would give me a standard deviation of 3. Well, what if the sample size, that's for n equals 9. What if the sample size had been n equals 16? Okay. What would our standard deviation for our sample distribution be instead? Anyone want to have a guess on that in the chat box? Based on what we know now, what would if I took repeated samples of size 16 and the population standard deviation was 9, what would my repeated, the distribution, the standard deviation of my repeated sample, my new distribution based on all of those sample means, what would be its spread? What would be its standard deviation? Oh, let's tell you, I'm going to check your work. It's going to be 9 sigma divided by the square root of 16, which is 4, okay, which is equal to, actually, I'm going to round. See if I can format cells. There we go. Okay, number. Good, that's good. Give us 2 decimal places. It's actually 2 1/4. Okay, how did I get that 2 1/4? Well, it's 9 sigma, right? Sigma divided by the square root of the sample size. So sigma for the population is 9. Standard deviation for the population is 9, right? Divided by the square root of 16, the sample size is 4. So 9 divided by 4 is going to be 2.25. Are we okay with that? Do I need to do another one? Would it help if I do another one? That a yes, no? Okay, we're okay with that? Okay. So what about if I had a sample size of 25? Okay. The standard deviation of my repeated sample, my sample distribution, right? Repeated over and over and over again, getting sample 25, finding the average, taking each number, now putting it into a new distribution, right? Doing it 100 times, 1,000 times, 1,000,000 times. What would our variability be in that new sample distribution? Well, it's going to be equal to 9 divided by the square root of 25, which is 5. So it's going to be equal to 1.8. That look right? I won't worry about that for right now. So I'm assuming it's right. Okay, so this gives us valuable insight into the way samples behave. Okay, and we're going to take advantage of this shortly. Okay, so let me see if I have some examples for you here on this original document. Okay, I think I can minimize this. Okay, where did my Word document go? Oh, this is my Excel document. Okay. Okay, good. Whoops. Okay, we just kind of went through this just a little bit, just a bit ago. And for instance, if the total cholesterol for a certain population are approximately normally distributed with a mean of 200 and a standard deviation of 20, we're going to answer a few questions. What's the probability an individual will be picked at random from this population to have a cholesterol value between 180 and 220? That's going to be 68%, right? One standard deviation above, one standard deviation above. How about 160 to 240? Two standard deviations above, two standard deviations below. That's going to be 95%. It's going to be the probability that you'd pick an individual in that range. How about greater than 225? Well, now we know we have to calculate a z-value, calculate number of standard deviations. Let's see if I can get this. Oops, that's not what I want to happen here. It's still protected. Okay, good. Oops. Let's see what that's going to be. So z is going to be equal to x, 225, minus the mean, which is 200, over the standard deviation, which was 20. Okay, that's going to be equal to 25 over 20 is going to be equal to 1.25. Right? So that's a positive 1.25 because it's to the right of the mean. It's 225 is the number we're looking for. So the question was, what's the probability that you would have a randomly select someone that's over 225, have the cholesterol over 225? Well, let's go to our Z table to look for that value plus 2.25. Oops. Table. See if I still have it open. Oops. Here we go. Nope, that's not the one I want. Okay, I'm going to come back to this one. So here's my Z table. So I'm looking for a plus 2.25 or 1.25. So let's look for plus 1.25. So that plus 1.25 is going to tell the area to the left of that value. So 1.25, 1.2, 0, 1, 2, 3, 4, 5. It's going to be an area equal to 89.44 or 0.8944. So I'm going to go back here, 0.8944. I'm going to write that down here just so I don't lose it, 0.8944. Okay, I'm going to say to myself, okay, that's the area to the left of 1 1/4 standard deviations from the mean, to the left of that value. But we're asking for the value that's greater than that. In other words, what is left to the right of that? So the answer is going to be 1 minus 0.89.44. Okay, which looks like it's roughly like 10.5% or something like that. Okay, you guys comfortable with that? 0.1065. Excellent. Perfect. Thank you. Less than 150. How about less than 150? Okay, z-score is going to be equal to 150 minus 200 is going to be 50 divided by 25. So that's going to be a z-score. Oh, excuse me, that's negative 50, right? Negative 50. That's going to be a z-score equal to negative 2. So negative 2, you know, I can use the empirical rule. The empirical rule tells me that 95% is between negative 2 and plus 2 standard deviations. So that would leave 5% left. That, since it's symmetrical, the normal distribution, that would mean 2.5% in the lower tail, in other words, less than 150, and 2.5% in the upper tail, more than 150. Now, here's where we discover that I told a little bit of a white lie. I'm going to actually look up the area that's represented by negative 2, a z-score of negative 2 or negative 2 standard deviations, and see what that area really is. So negative 2, negative 2.00 is actually not 2.5%, it's 2.28%. So the empirical formula is really an approximation. It doesn't give you the exact value, but it gives you a rough value that's useful when you want to do some quick calculations or make some casual judgments or something like that. But in reality, the real answer to that question is the probability of selecting someone who has a cholesterol level below 150 is 0.228 or 2.28% of the time. And between 150 and 210, So this is 0.22, oops, 0.02, what was it again, 228, I think. Yeah, 0.228, right? And between less than 150 or more, less than 150 or more, but how about between 190 and 210? Well, 190 is half a standard deviation below, and 210 is half a standard deviation above, and you can actually look up a z-score of plus 0.5 and minus 0.5 and see the area between them. So I'm going to do that because it's an interesting issue. So what's the area between these two? Well, I'm going to start with 210. The z-score for 210 is equal to, for 210, z-score is equal to 210 minus 200 over 20, was it 20? I think 20, right? Okay, so that's going to be equal to 0.5, a plus 0.5. So what area does that represent? That represents an area 0 plus 0.5. That represents an area of 69.15%, 0.6915. Okay, and what about the area? So the area to the left of 210 is 69%. What about the area to the left of our next, the next value we're interested in, which was 210, so, which was 190. So 190 minus 200 over 20 is going to be minus 0.5. So what area does that represent? Well, I'm going to go back here and look for minus 0.5. Minus 0, oops, minus 0.5 is 30.85, 0.3085. 0.3085. Okay, so this is the area to the left of 210. This is the area to the left of 190. So the area between those two is just simply this area minus 0.3085, right? So I'm taking the area, that larger area, which you can kind of see illustrated here. Let's say that this was our 69% for our z-score plus 0.5. Our z-score for minus 0.5 is here. So if I take this area, 69%, and subtract the area that's represented below negative 0.5 z-score, well, then that leaves the area between those two, right? So all I have to do is subtract the 0.385 minus 0.3085, and I will get the result for our calculation. Anybody have that? Did anyone do that? 0.383. Good. Thank you very much, guys. Excellent. Good. I'm glad you guys are working on these calculations along with me. Okay, so let's take a look at another exercise. Okay, so now we're going to get back into the central limit theorem, and we're going to get into why the central limit theorem is so important to us. I just want to take a quick look ahead here. Okay, so, applying central limit theorem. We take a sample of size 25 from that same population. What do we know about that population again? We know that the mean is equal to 200. That's mu, right? That's the population mean, right? We said it was population, so we refer to that as mu. And the standard deviation, we refer to as sigma. We didn't draw it there, but we mentioned it was population parameters. There's 20, so that's mu and sigma is 220. Okay, a sample of size 25 is taken from the population above. What is the probability that the mean of that sample is larger than 204 per 100 milliliters? That's the units for per 100 milliliters of blood, the units for cholesterol. In other words, cholesterol is larger than 204. Well, let's think about that for a second. If I took repeated samples of size 25, what would I expect that distribution to look like? Okay, well, we know that we would expect that the population mean, the X bar, the mean of all the repeated sample means, we'd expect it to approximate the same mean as the population. Okay, let's say approximate 200. Okay, but the standard deviation of this new distribution that's made up for these samples of sample size equal to 25. The standard deviation is going to be much narrower, right? It's not going to be as wide as the normal population. It's going to be equal to sigma 20, the population standard deviation, divided by the square root of the sample size. Okay, let's calculate what that's going to be. That's going to be equal to, it's going to be equal to 20 divided by the square root of 25 is 5. So the standard deviation for the repeated samples is going to be equal to 4. Okay, so our standard deviation for our sample distribution is 4, with a mean, expected mean of somewhere around 200, right? So that's interesting now, because now I can make predictions about how likely it would be that I would get, if I took a sample of size 25, that I would get an average for that sample of 190, 200, 210, 215, and so on and so forth. I can make a prediction of what our sample would look like from this population. Okay, it's a little bit backwards because I'm working the other direction. I know the population standard deviation and standard deviation. You want to know something? At this stage, in order to not get confused, in order to not get confused, boy, you guys are ahead of me already. In order to not get confused, I am going to stop calling the population, the standard deviation for the repeated samples. I'm going to stop using the term standard deviation for that, because that sounds like it's a single sample standard deviation, which approximates the population standard deviation. It really isn't. It's a new standard deviation. What it would look like if we took repeated samples of size 25, I'm going to give that a new name. I'm going to call that the standard error. And the standard error is based on sigma over the square, sigma for the population over the square root of the sample size. So what's the question here? The question here is, what's the probability that we would take a random sample of 25 people and we would get a mean for that sample that's larger than 204? Well, now we have a new distribution we're working with. Oops. The new distribution that we're working with has a mean equal to 200 and a standard error equal to 4, not the standard deviation. So what is our z-score? What's our z-score going to be for a sample of 204? So that's going to be equal, that z-score is going to be equal to, the value we're interested in minus x bar, right? Because we're dealing with a sample now, divided by the standard error. Okay, so what is that going to be? That's going to be, let's see, x is going to be 204 minus, 204 minus 200 divided by the standard error. And the standard error is equal to 4. So that's going to be equal to 1. Right? So one standard error or one standard deviation for the sample population. So what's the probability that we would get a mean that's more than, did it say more? More than 25? More than 204? There's a probability that the sample is larger than 204. Well, I'm gonna use the empirical rule here. This is a standard deviation of 1. So the probability that I would get a value between one standard deviation above the sample distribution, the sample mean, and one standard deviation below the sample distribution mean is 68%. That would leave 16% above that z-score of 1. So the chances of us taking a sample of size 25 from this population, which has a mean of 200 and a standard deviation of 20, the probability of us getting a sample that has a mean above 204 is about 16%. I could actually look it up exactly in the Z table, but I'm going to be satisfied with the empirical formula. So what is the probability that we would get a mean sample that's between 192 and 204? Well, geez, I wish I could draw this a little bit. We're going to take a break shortly. I'm going to see if I can't get to something that will allow me to sketch on this laptop that I've borrowed. Okay, so okay, what's that? 16? I'm not sure what 16 refers to, but oh, 16%. Yes, thank you very much. Okay, you're absolutely right. I kind of moved on, my brain moved on from there a little bit. Okay, well, what about 190? What about that 90? And I'm gonna just interpret this for us. So what's the probability we would get a value between 190 and 204? Okay, well, we know that 16% of the population is above 204. 16% of the samples, possible sample results, sample means above 204. And 192 is 2 standard deviations below, and 2 standard deviations below, 2 standard deviations above represented 95%, right? So we have 16% above, but with 95% of the distribution being between 192 and 208, right? That means that below 192 is only 2.5% of the population. So 2.5% of the population is below 192, and 16% of the population is above 204. So that accounts for 18.5% of the population, right? I'm going to call it 19% of the population. So that means 81% of the population is between 192 and 204. The population being the possible means of size for sample size 25 from this population. Okay, a little confusing, right? But it's important that we understand that this is going to give us, this is an immense tool for us, because now we're starting to understand how sample did. Okay, we could just. Okay, great. Thank you very much. Okay, excellent. Okay, I want to go through some of the lecture material. There's a PowerPoint on Blackboard, and I just want to go quickly through that before we go back to some additional examples. Okay, so I'm going to start by describing what we're talking about here is examining sampling variability, how samples work, and considering the central limit theorem. So central limit theorem is what allows us to understand the relationship between the population mean and standard deviation and the distribution of samples from that population based on different sizes. So there is a different sample distribution for a given population for every different sample size. If the sample size is 10, that has a unique mean standard deviation or spread if we take repeated samples of size 10. If the sample size is 25, that has a unique sample distribution, sample mean distribution. If you take repeated over and over again samples of size 25 and then plotted them on a histogram or a normal distribution. Okay, so we're going to take a look at this. We're going to take a little bit of a look at how we applied this to certain studies. Okay, so first of all, keep in mind that we're always using samples to infer information about the population. So our sample is a random selection of people from a population. Our sample mean, we term X bar. And from that, we infer certain things about the population mean, in other words, mu. So generally what we're trying to do is we're trying to demonstrate that the sample mean approximates the population mean. So we can take a sample, not have to examine every person in the population and get a reasonable approximation of what the population mean is. Now, the only downside of that is that if I take a sample of 25 people from this population, it looks like Massachusetts. If I take a sample of 25 people, well, you know, I could be pretty far off if it's a small sample and I'm generalizing it to such an enormous population. In this case, a small sample came up with a mean of 67 in the ballpark, but not all that close. Well, how about a larger sample? A larger sample came up to be 71. And an even larger sample came up with a mean of 75. So the larger the sample size is, the more reliably, the closer to the real population mean that we expect that we would be. It's not a guarantee though, right? Because anytime we take a sample, we always have the chance that we are going to just wind up sampling more people that are above the mean than are below the mean, and our average is not going to be exactly the same. In fact, it would really be unusual to have a mean that a sample mean that turned out to be exactly the same as the population mean, right? That would be a rare bit of really good luck. Close, yes, but not exactly the same, right? Wouldn't happen very much. Okay, so we use samples to determine a mean and a standard deviation of a sample so that we can infer that the mean and the spread, the standard deviation of the population, is similar to that. Okay, so the sampling units basically are the individual people within that population that we're sampling. The target population is the population that we want to describe by taking samples. In other words, a target population is going to be, for instance, if we're interested in males from 20 to 40 years old in Massachusetts, that would be our target population. The study population is the actual sample of people, the population that we actually sampled in order to make our inferences, right? And the sampling frame is a list of all of the results in that study population. In other words, all of the individual results. Now, you don't have to worry about that too much, but keep in mind that sampling, we're going to randomly sample most of the time. We're going to want to do random samples, but a lot of times that's not going to be that easy to accomplish. Okay, we already saw that was a little tedious, even just working with a list of numbers. Okay, notation. Anytime we talk about a population parameter, some statistic that describes the entire population that we're targeting, we're going to use the symbol mu for mean and sigma for standard deviation. Anytime we're describing the distribution of a sample mean, the mean is going to be X bar and the standard deviation is going to be either S or SD. Okay, so those are going to distinguish. One is a parameter, mu and these are parameters, mu and sigma, and for the actual sample itself, the mean and standard deviation is X bar and S. Samples versus parameters. Okay, so sampling strategies. Once then, we just applied a simple sampling strategy to start off with, right? And that sampling strategy was just randomly select people from the population. That might be done based on social security numbers, randomly gathered, randomly making phone calls, and so on and so forth. But that's one strategy we might use in order to sample a large population, to just simply get as random a sample as possible. Okay, systematic sampling is a little bit different. So for instance, maybe we decide that we're going to in a list of people, we're going to sample, we can't afford to work with every person. So we're going to sample every 30th person in that target population. So the first person, the 30th, the 60th, the 90th, and so on and so forth. In a sense, that's kind of a random sample, just by virtue of the fact that there's probably no connection between those people, those individuals that you're sampling in that manner. Not exactly a random sample, but it can very frequently wind up being close to a random sample. Well, how about stratified sampling? let's say we wanted to find the average age of people in New York City. So we decide we're going to randomly sample 100 people, right? And we look up, we call up a bunch of people, we ask them their age and so on, and we wind up with 100 numbers. But you know, in addition to taking that information, we also took some other information like gender and borough of residence, for instance. So let's say when we've taken our random sample based on a phone survey or some other way that we're doing it, right? We wind up with 100 people that responded with their age, and we notice that the distribution of gender is 40% female and 60% male, just by chance. And we say to ourselves, oh, you know, I know in New York City's population that, you know, that historically there are more females than males. They tend to live longer. There are more of them and so on and so forth. So I've oversampled males and undersampled females by accident. Well, you can avoid that by doing a stratified sample. So for instance, if you're interested in the average age in New York City and you're concerned that if you take a random sample that you'll wind up with too many people from Brooklyn and not enough people from the Bronx, what you can do is you can say to yourself, well, the population of Staten Island is 20% of the entire population of the city of New York. So instead of we're going to take a random sample of 100 people, I might say to myself, well, I'm going to take 20 randomly sampled from Staten Island and 25 randomly sampled from the Bronx and 30 randomly sampled from Manhattan. I'm going to wind up over 100. I didn't mean to do that. And another 31 from Queens and maybe 35 from Brooklyn because Brooklyn's the most populous borough. So I want my sample distribution to match the true population in New York, not oversample one particular borough or the other. It's really a random sample, but it's random sample within each one of those strata. Okay, so we have a number of sampling strategies based on that. Okay, so I'm gonna move on to a bit from that. Okay, so let's take a look at this histogram. Okay, this histogram represents the running times. Each one of these bars represents a range, a bin or a range. This represents the running times for all 16,924 participants in a 10-mile ride in Washington, D.C. Cherry Blossom Run, so you know it's in the spring. Is this a sample or a population? It represents all of them. What is that, a sample or a population? I'll ask you. Sorry to wake you guys. Is that a sample or a population, that histogram? I know you're still there. I can see you. I don't know if there's a lag or I'm losing you guys. I notice we have, guys, remember to mute your microphone if you're logging in so that we don't get a lot of background noise. And warn me if you're getting background noise or an echo or something like that, warn me so that we can make sure that the recording works well. Anybody want to hazard a guess? Well, this is a population, correct? We're looking at all of the people. The highest bar is over 4,000 people, represents over 4,000 people, right? And that the time there was between, looks like it's between 90 and 100 minutes to complete this 10-mile run. And this is different. Some people completed it much quicker, but very few. Some people took much longer, but very few. Most of the people are clustered around in the center. This is typical of a normal distribution. Okay, so this is a population sample. Okay, so do we refer to the mean of this, the average of this, as mu or as X bar? Well, since it's a population distribution, the mean is mu, not X bar. So the mean's probably going to be somewhere around, looks like to me, about 95 or something like that. And that would be mu is equal to 95, not X bar, because X bar represents a sample. Okay, let's take a look at this. So in this one, I can see that this is our initial population distribution. 4,000 people. This is like 2,000 people, 2,100 people, 2,400 people, so on and so forth. This represents all 16,000 runners. This represents a sample of 100 runners randomly sampled from this population. And look, it's only 100 people. So in this bin, there's only about 27 people. In this bin, there's only about 16 people, and so on and so forth. So this represents a sample of 100 people plotted as a histogram. This represents the entire population of 16,000 people. It's a random sample and population. Notice that they're kind of similar. The middle is in roughly the same space, and the spread goes from 40 to about 150. So it's roughly the same spread as well, right? So the sample distribution mimics or is similar to the population distribution when we take a sample. And that's why sampling is so effective. Okay, so what's a sampling distribution? It's when you take a random sample from a population and you calculate a sample statistic like mean and a standard deviation, because you know that that will approximate the population mean and standard deviation. So you have a tool to understand that, or at least get a rough idea what it might be. Okay, so what about if I take, instead of taking, let's see, okay, so let's say that I take repeated samples of size 25 from a population that has a mean serum cholesterol level of 211, right? And a standard deviation, let's see, cholesterol level, size 25 for serum cholesterol levels of 20 to 74-year-olds. So look at this. The sample distribution, the average, it looks like the average serum cholesterol level for this population, this is the entire population, is 211. And we had people that were as low as 73 and as high as 349. So the population distribution was very flat, wasn't it? It was very spread out. There were people that had a wide range of cholesterol levels. None really, not very many below 73, not very many above 349, but pretty spread out. Well, now let's say we took a sample of size 25 from this population over and over and over and over again. And this time we drew a new normal distribution, a new sketch for a normal distribution, where the new sketch represents the variability in the center for the sample means. In other words, 25 people get a sample mean, 25 people get a sample mean, 25 people get a sample mean, and now take those sample means and display them as a graph. Okay, well, that's what this looks like. The middle mimics the middle of the population. So the middle, half the time, we'll wind up with a sample mean when we take a sample size 25. Half the time our result will be below 211, half the time will be above 211. So our overall mean for our repeated samples is going to be the same as it might be for the entire population. However, our spread, since you're taking a sample of size 25 and you're calculating a mean, you're automatically going to get a result that is less variable than if you picked any individual. In other words, if I took 25 people randomly and calculated what the mean for those 25 people is, it would be very rare that you would ever get anything as low as 73 or even 119. You would expect it to be much closer to 211, all of the values, because sampling is going to do that. It's going to give you a narrower variability. And in this case, this illustrates it. This tall, skinny one is the sample distribution for sample size 25, repeated sample means for sample size 25. And this flatter curve represents the population normal distribution. Okay, let's take a look at this one. Okay, now let's see what this looks like. Okay, so here is our sample for all 19,000. Here's our histogram for all 16,924 runners. The mean is equal to 36. The median is equal to 33. And the standard deviation is equal to 10. The mean and the median are not exactly the same. It looks like it's skewed a little bit. The mean's a little bit higher. What's happening is some of these high values here are skewing the mean upwards. So this is skewed to the right slightly, but it's pretty close to a normal distribution. So now what if we took 100 runners and made a new sample distribution from that? Well, what happened? We got a mean of 35, very similar to the population. We got a median of 33, very similar. We got a standard deviation of 9, which is very close to 10. So when we take a sample from a population, the spread, the standard deviation, the mean is going to be similar or approximate the population standard deviation of mean. Now notice this is not a distribution, a histogram representing a distribution of repeated samples of a certain size, right? It's just 100 runners. It's one sample of 100 runners with a histogram showing you what the values were for those 100 runners. So this is what a sample of 100 people from this population looks like. But it's only one sample with a mean of 35. It's only one sample, not repeated samples. What happens when you do repeated samples? When we do repeated samples, the central limit theorem tells us that the means that repeated samples from and the new distribution and its new distribution based on those repeated samples from a population is going to have a mean that approximates the mean of the population, and the sampling distribution, right, X bar and the mean are going to be similar, but the sampling distribution is going to have the relationship to the population standard deviation of sigma over the square root of the sample size. Bigger the sample size is, the less variable your repeated sample means are going to be, less different they're going to be from one another. So SE represents standard error to mean, which we know to be the standard deviation for repeated sample means. Okay, so, and this is another illustration of those two charts. Okay, so the larger, now the other thing that the central limit theorem tells us is that as the sample size goes up, so in other words, here's a sample size of 1. So we have a population here that basically isn't even normal. It's just spread out like this, right? There's almost no organization at all. Well, if I take repeated samples of size 4 from this and plot the sample means, notice how it starts to form a normal distribution. As the sample size gets bigger, the distribution becomes even more normal. So what does that tell us? That tells us that the central limit theorem, the idea that we can use this understanding of samples to not only approximate the mean of the sample, but also approximate the standard deviation and the repeated samples from that, the means that are now that we've gotten from those repeated samples from that population, that those means are now going to be more normally distributed than the original population is. So for central limit theorem to work, we don't have to have an original population that's perfectly normally distributed. So that's a big advantage for us, because a lot of times we're going to be working with populations that aren't perfectly normally distributed. Okay, so keep in mind, standard error represents this variability in repeated samples. So the larger the sample is, the narrower the spread is, the standard error is a smaller number, and the more symmetrical and more normal that it is. So we want a big sample to have, big sample. So what is a big sample? How do we define a big sample? Well, we're going to get into a lot of debate here. You'll read a couple of textbooks will tell you different things. But for the most part, you start to think of about, if you want to know about it, if you're going to predict a sample that satisfies central limit theorem reasonably, you start to be looking for a sample size of 30 or larger. Now, a lot of books will say, well, a large sample might be 100. For instance, you might want to define it as 100, but certainly more than 30 would be considered a large sample, and often maybe 100 or a couple hundred would be a large sample. But you can get a lot of information from samples that size without having to go even bigger than that. Okay, but it's going to depend a lot on what you're going to be looking for. Now, you know you can do the same thing with a proportion. Okay, let's say that we have a population that has who has a that the percentage of left-handers in the population is 30%, right? So if I randomly sampled one person from this population, the probability that I would get someone that is left-handed is 30%. Probability that they're right-handed is 70%. Okay, so now what about if I took a sample, repeated samples of size, say 100 from this population, from that population, right, where it's 30% left-handers, right? Let's say we didn't know that 30% of the population was right-handed. We had no idea about that, right? So what we can do is that we can say to ourselves, well, let me take a sample of size 100, and maybe we get 27 people are left-handed, maybe 31 people, and so on and so forth. But that is our sample proportion. Just like I put an X bar for our mean, we put a little cap over the P to represent our sample proportion. We just use P to represent the population proportion, which we know to be 30, which we secretly know to be 30%. So we can do the same thing. We can plot repeated samples from a population for a binomial variable, for a proportion. We can plot that like this, and we can determine what the probability is that we would get a proportion above or below that mean. In other words, we would be able to predict what the spread would be. So spread is a standard error for these repeated samples. So the spread, the standard error for a proportion, is equal to the square root of P, which is the proportion from your sample of people that are left-handed, times 1 minus P. Let's say it's 28%. 1 minus P would be 82%, 72%, right? Over the sample size, which for our purposes we said was 100. Take square root of the whole thing, that gives you a standard error. And you can predict that if you took repeated samples from this population of size 100, you could use this standard error to say, tell you 95% of the time, if I took another sample of 100, it would be between 2 standard deviations below, 2 standard errors below this, my P, my proportion, and 2 standard deviations above. Well, what does that do for us? That does a few things for us. That also lets us figure out what the likelihood is that we would get a certain percentage, a certain value or proportion or certain mean or proportion given that our population is unknown. So since we can take a sample, and the sample gives us an approximation of the population mean and an approximation of the population standard deviation, we can say to ourselves, well, what's the likelihood I would have gotten a similar result if I took this sample again, right? And that can give you an idea of what the range of possible samples would be if you kept sampling over and over again. But you can use that to help you make a judgment as to how accurate your sample is when you take a single sample. Because we understand how sample means behave, we can now make some inferences with that. We can count, we can't say, for instance, if I take a sample of people and measure their blood sugars, and I sample 100 people, and I find the mean, sample mean, X bar is 67, and the standard deviation is say 10, right? I can say to myself, okay, it's 10. Now sample size is 100, so my standard error would be 10 divided by the square root of the sample size, which is 100 is 10. 10 over 10 is 1. So my standard error is 1. So it seems like that if I took another sample from this population, My standard error is 1. The value that I got was 67, approximating the population mean. So I can kind of get the feel that 90, if I redid that sample, the chances about 95% that the second result I would get would be between 65 and 69. 2 standard deviations above and 2 standard deviations below the mean. In this case, we're actually talking about 1.96 standard deviations above and 1.96 standard deviations below. That z-score is what is represented by exactly 2.5% on the left-hand side, 2.5% on the right-hand side. In other words, from our empirical formula, the -2 and the +2 is really only an estimate. The true z-score that would give you 95% above and below the mean is -1.96 and +1.96. I could actually show you on the table that actually works out. I'll see if I get a chance to do that. Okay, so let's take this to the next step. What does this allow us to do? And what this is going to allow us to do is calculate something called a confidence interval. Okay, and a confidence interval is a range that we can predict based on a single sample and our understanding of how samples work and their probabilities. We can predict that that the true population mean, even though we don't know what it is, even though we don't know how close we are to it for sure, right? We can predict that whatever result we got from our sample mean, we can predict that we're 95% certain that the true population mean is between 2 standard deviations below the mean, that sample mean, and 2 standard deviations above the mean, right? Now, and that standard deviation really is standard error. In other words, sigma for the population over the square root of n. Sometimes you'll know sigma, most of the time you won't. So instead of sigma, use the standard deviation for the sample that you took, just like you use the mean for the population, for the sample that you took. Okay, so we're getting in pretty deep here, right? And I don't want to get too far ahead on this. I just want to go over study designs and then maybe close out with a single 1 or 2 examples of how we might apply this to confidence intervals so that you have something to look forward to on Monday when we move on to confidence intervals, which is the first chance that we're going to get to do real statistics, real predictive statistics, real inferential statistics. Okay, so let's take a look at the study designs. First of all, an observational study is something like a census, right? You actually look at a cross-section of an entire population, and you don't actually do anything. You don't give them a drug. You don't put them through some intervention. You don't give them a blood test. And so, well, maybe you might give them a blood test, but there's no actual intervention. You just make measurements. So cross-section, an observational study, cross-sectional observation studies is a random sample of the population at a point in time. So our New York City Haynes, our nutrition survey, New York City Community Health Survey, those are cross-sectional. A retrospective observational study is subjects are you're going to examine subjects who you know have had some experience in the past. They've had cancer, they have lung disease, they're smokers, they're within a certain age range. So retrospective is people that had some exposure in the past. Prospective is going to be studies of people that you're going to follow forward to time. So retrospect, you're looking at things that happened to subjects in the past, and we'll see how that works. And prospective is things that happen that are you're going to follow subjects and observe what happens in their health status as you move forward. We'll take a look at a couple of those in a second. Observational studies can't prove causality. They can give you an idea that there's an association between an exposure and some outcome, but they can't prove causality. There's only one kind of study that really proves causality, and that's an experimental study. What is experimental studies? An experimental study is when you divide up subjects into two groups, and one study has an intervention. For instance, you test a cancer drug or something like that, or a blood pressure drug, and the other study gets a placebo or is a control group, right? And you randomly assign people to those studies, to those two studies. Okay, so the experimental studies, you have the opportunity to actually show that giving a person this drug causes a better outcome than giving them the placebo, or giving them this drug lowers their blood pressure versus the control group where it had no effect, and so on, right? So you can predict, you can like use that study to predict causality. Okay, so how about you randomly assign smokers to no intervention or cessation program? You follow them prospectively. You follow them to see years later which of the two groups had more cases of cancer. That would be an experimental study. Okay, okay, so observational study cross section. Oh, no, maybe not. Okay. Now, again, going back to observational studies. Retrospective, you might recruit 50 people, 50 cases of lung cancer. And let's say that you that you are associated with a clinic and you want to see if there's an association between lung cancer and, say, smoking. Well, you might go to that clinic. Maybe they treat people for many conditions. Maybe it's general practitioners and so on and so forth. But you look through their medical records and you determine there are 50 people. Maybe it's a company. Let's say it's a company, right? You go to company's medical records and you look and you see that you have 50 cases of nasal pharyngeal cancer in that study, in that company. So you have people that have gotten lung cancer or nasal pharyngeal cancer in the past. You have 50 of them. So now you take 50 other people, same age range, same company, work for the same company, and so on and so forth, except maybe you're looking for 50 people who don't have lung cancer, but now you know that the people in that company, some of them work directly on the production floor with where they're exposed to nickel or cadmium dust or something like that, where a lot of people work in the offices and in sales and they don't have that exposure. So now you compare your 50 cases, people have lung cancer, to the 50 controls who do not have lung cancer within the same group, within the same cohort, and you say to yourself, well, how many of those 50 people who had lung cancer, developed cancer or nasopharyngeal cancer, how many of them worked with the nickel? And of the people that don't have lung cancer, how many of them worked with nickel? And you would expect that you would have more people who worked with nickel in the 50 cases with lung cancer versus the 50 people who didn't have nasopharyngeal cancer, right? So you would try and use that kind of, that would be a retrospective study. The good thing about that kind of study is that you already have the data that you need to complete a study like that, because you already have people that have had the exposure and have the outcome. So all you need to go through is records to determine which group people fit into. A prospective version of an observational study is when, for instance, you observe groups of smokers and non-smokers for many years. You might have to follow them for 30 or 40 years to see which group develops lung cancer more frequently. So that would be an observational study, but it's prospective, where the one where you're working with people that have already had cancer versus people that are similar to them in most other variables, didn't develop lung cancer, and you examine what exposures that they may have had that may have disadvantaged the group that had the cancer diagnosis. Okay. So just to finish up, I'm going to finish up now. And just to finish up, I want to quickly go over, I want to quickly just do a quick problem that gives us an example of a confidence interval. So you can kind of prep yourself what's going to go on next week. Okay, just so you know, this is the point, the central limit theorem. I think this is going to be the point where I think the exam is scheduled for Wednesday. Am I right about that, guys? Is Wednesday the date of the exam? Or at least when they make the exam available online? After Wednesday, I think. I'm pretty sure. So this, and maybe a little tiny bit of the calculation of confidence interval, is the point where I think we'll wind up going at this point. So going as far as the limit on the test. Okay, so I just want to introduce this idea of confidence interval. First, I need to get this out of the way. Yeah. Not cooperating. Let me close this. Come on. Nope, I don't want to do that. I can't get to the screen here, unfortunately. Let me close all of these. Get out of this whole thing. Okay. Okay. So the weights, we're gonna do a study, and the weights of adult males from 18 to 65 is approximately normally distributed with a standard deviation of 30 pounds. This is the population standard deviation, sigma. Now, are you always going to know that? Nah, you're not always going to know what sigma is. But for our purposes now, for our first look at confidence intervals, we're going to say that we don't know what the true mean is. We don't know what mu is. Mu is unknown to us. Mu is an unknown to us. But we do know what sigma is. Sigma is equal to 30 pounds. Okay, so now we take a sample of 25 men from this population, and we find that X bar is equal to 150 pounds. Okay, well, 30, remember we said 30 is not, a sample of 25 is not a gigantic sample. It's getting pretty close to a large enough sample to have some confidence in. But 25, it's still a pretty small sample. However, we have the advantage of knowing what sigma is. And what that tells us is that if we were to take repeated samples over and over again from this population of size 25, sample size 25, over and over again, the variability in our sample means would be equal to, what's it going to be equal to? We call it standard error now instead of standard deviation. Standard error is going to be equal to sigma over the square root of the sample size. I'm going to write it this way. It's a little bit easier. That's the way you would type it into Excel. So what is that going to be equal to? It's going to be equal to, in this case, 30 divided by the square root of 25 is 5. It's going to be equal to 6. So that's the amount of variability that we would expect if we took repeated samples over and over again, variability in the mean, if we took repeated samples over and over again in a population that had a standard deviation of 30, sigma of 30. So our standard error is equal to 6. So now our mean came out to be, for our sample of 25 people, came out to be 150 pounds. So now we'll never really know how close that is to the true population mean, because we're never going to know what the true population mean is. However, because we know something about the way samples behave, in other words, the variability of sample results, right? We can take that sample result and we can now make some predictions about that'll help us understand what the true population mean is likely to be. And instead of being able to say, oh, we're within 2 pounds of the population mean or within 3% or something like that, what we're going to do instead is we're going to produce a range of values that we know the true population mean, based on this variability, true population mean is likely to be within that range of values. So I may not be able to say how close I am to the actual mean or what the actual mean is, but I may be able to say something like, I'm 95% sure that the true population mean is between 140 and 160, or perhaps 130 and 170, right? That has some value in it. Now I can make a prediction about, where I have some level, understand the level of certainty I have about my result. Okay, so we're going to do that here. And how are we going to do this? Well, we're going to say to ourselves that our X bar, right? I'm going to start with our X bar. And then I'm going to say to myself, well, how far below my X bar and above my X bar would I expect to have to go in order to predict my confidence in my 95% confidence interval? Well, on 95% confidence interval in the empirical rule, 95% of the outcomes for our repeated sample means, well, that's empirical rule tells us that's 2 standard deviations above and below. So I'm going to say plus or minus something, we'll add or subtract 2 standard deviations. Now for a sample mean, we use standard error. So basically my 95% confidence interval is going to be the mean for my sample plus or minus 2 standard errors below the mean and 2 standard errors above the mean. And I'm 95% sure the true population mean is between those two, right? So I'm going to say, okay, what's that going to be? That's going to be 150 plus or minus 2 times standard error is equal to 6. So what is that going to be? That's going to be 160 plus or minus 12. So my 95% confidence interval, 12 less than that is 138, comma, and 12 above that is 162. So given this information, what we know about sigma and about our sample mean, we're 95% confident that the true population mean is between these two numbers. Let's say that's pretty interesting, but you want to know something? This is a little bit of a lie again. Really, X bar plus or minus, okay, not 2 standard deviations for 95%. What do you guys remember what it should have been for 95%? 95% of a distribution, what should it have been? You may be typing in there and I can't tell. Let me make sure I can see when you're typing in there. Oh, you are typing in there. You are following me. I got 2 standard deviations from the idea of the empirical formula, right? Empirical formula says 95% of the outcomes are going to be within 2 standard deviations above and 2 standard, but I lied, right? It's not really 2 because the empirical formula is only an estimate. What is the real number I should be using instead of 2? You guys remember what it was? Right? And you want to know something? I'll show you what it is. What represents, let's see, the standard normal distribution. Here we go. Let's open that up. Oops, no, I don't want that one. That one's nasty. Okay, let's see. And my Z table. Okay, here's my Z table, and I want to know, if I can't get this to go away. Okay, and I want to know, for instance, what Z-score, what number of standard deviations represents an area to the left of 2.5% and an area to the right of 2.5%. Let's see what it's going to be. Let's look for the areas now. Let's look for the areas, not the Z-scores. Where is the area 2.5% located here? So the area 0.250 is, where is that? Okay, it's going to be around, here it is right here. I don't know if you can see my cursor. It's kind of light here, but here it is right here. Can you see it there? Okay, that is equal to a Z-score of 1.96. So it's not really 2. 2.5% to the left and 2.5% to the right is really 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. So my real formula for my confidence interval is X bar plus or minus 1.96 times the standard error instead of 2. I won't work it out. It's just a matter of multiplying it out. It'll be a little less. It'll be probably 138.2 to 161.8 or something like that. It'd just be a little bit narrower because it's 1.96 instead of 2. But that would be my real value. Well, what about if I wanted to know, if I only wanted to be 90% certain? If I want to only be 90% certain, then I would be wanting to look for the number that would represent an area where you got 5% outside, below, and 5% above. So I'm 90% of the outcomes would be between those two numbers, between those two standard errors, between so many standard errors below the mean and so many standard errors above the mean. 5% on each side would be 90%. And that would be a confidence interval, 90%. Let's see if I can't find 5%. So 5%, closest one to 5% is down here, right? And that is 1.64. So if I want a 90% confidence interval, the formula would be instead x bar plus or minus 1.64 times my standard error. Or in other words, 1.64 times 6. Okay, and if I actually did that calculation, well, I'm going to just give it a, let's see, 369. I think that's something like 9, right? So I'm just going to quickly write down here. That's roughly, x bar is 150. So this would be roughly 141 to 159. Is my 90% confidence interval, wider or narrower? Is my 90% confidence interval wider or narrower than my 95% confidence interval? It's narrower, isn't it? Right? Why is it narrower? Why isn't it wider? What's happening there? What's happening there is, if I'm willing to accept more chance of being wrong, in other words, I'm willing to be only 90% confident that my true population mean is between these two numbers, I can have a narrower range. If I want to be more confident, let's say I want to be 99% certain. If I want to be 99% certain, I have to make my range wider to make it so that I'm more certain that I'm going to capture the true population mean between those two numbers. So in fact, just so you know, I'm not going to bother to look it up on the table, but if you want a 99% confidence, you would do x bar plus or minus 2.54, or maybe it's 2.58. Let me make sure. This would be 99.05. 0.050 would be 0.050. 2.58 would be 2.58 standard deviations above and below the mean. 2.58 times the standard error, right? So that would be 150 plus or minus 2.58 times 6, our standard error, right? And that would be, let's see, 2.5. That would be 12, and 3, it'd be about 15. So that would be roughly about 145 to 165. So if you remember these three numbers, you will be able to remember how to calculate the 99% confidence interval, the 90% confidence interval, and the most frequently we used one, which is a 95% confidence interval. And you guys have already seen studies like that. I'm sure you have memories of reading a study where it'll say that they took a random sample of 100 children in the Bronx and measured the blood lead levels, and the results were 4.3 micrograms per deciliter of blood. And then in parentheses next to that, it had 95% CI is actually 3.5 to 6.2. In other words, the average they got for those children that they tested was 4.6. But based on the variability of the results that they have, and the level of confidence that they want, they're saying that, yeah, we measured the average was 4.6 for the children we tested. And based on what we saw, we're predicting that we're 95% sure that the true mean population mean for all the children in the Bronx that have this exposure is between 3.6 and 6.1 or something like that. That's where you use the confidence interval. And this is the first bit of statistics, besides, kind of basic descriptive statistics. This is the first bit of statistics or inferential statistics that we've run across that you see used all the time in real life. Yeah, 99%. Okay, so 99% confidence, right? So what does that mean? We want to make sure that we're 99% of the possible outcomes of these sample means is going to be within this range. So that means you have 1% that's going to be outside of that range. So remember, it's symmetrical. It's got to be symmetrical on the bottom and the top. So symmetrical on the bottom and the top means that the bottom has to be 5% of, whatever value it is, 5% left, half of 0.005, half a percent, and the upper part has to be 0.5%. So all we really need is go to the lower part, because it's going to be symmetrical. It's going to be the same number at the top. Let's go find 0.005 or 1/2 of 1%. What area? Where is that? Okay, so let me move this over a little. Okay, so where is that? Let's see if we can't find it. 0.005. Well, the closest I got is 0.051 or 0.049. I'm going to just pick this one out. So what is the z-score that gives you 0.005 or this is as close as we're going to get? Well, that z-score is negative 2.58, right? Can you see it there? Negative 2.58 is what that z-score is. And you know that if you went the other direction to 99.5, you'd get the same thing on the other, same value on the other end, 2.58 is going to represent 99.5. That's the other 0.5% is above that and below that. So that's where we get that 2.58 from. Just like we got the 90% from the value on these Z table that would give us 5% below and 5% above, 5% area below and 5% above. Okay, guys, I think that